Test. Very good. All right, so today we're going to continue with lecture set number 4, which is discussing the one-way ANOVA procedure. Once we finish lecture set number 4, we'll move into lecture set number 5. Lecture set number 5 is actually very closely related to the lecture set, the 4th lecture set. So basically, once we complete the examples on how to run the ANOVA and we go over the interpretation of the result from the ANOVA, the natural question is going to be, how do we actually determine which means are different? And how do we actually use residual analysis to check the assumptions of the procedure? And that's what lecture set number 5 is about. So it's a very similar topic. It's kind of the an extension, if you will, of the one-way ANOVA result. Okay, so last class, we spent the majority of the lecture discussing the steps of the ANOVA, the one-way ANOVA, and discussing the rationale for why you can use variances to make a statement about the population means. Okay, so we left off finishing this example that's shown on slide number 26. So we have our 6 steps of the one-way ANOVA hypothesis test. On step 1, we have the null hypothesis that the 4 means are equal against the alternative that not all the means are equal. On step 2, we state our significance level. On step 3, we compute the test statistic. Okay. And again, as you can see here, the test statistic is computed using an ANOVA table. On step 4, we can take either the critical value or the p-value approach. These are using the F tables now, but they are essentially run in the same way that, the F table works very similarly to how a T table works, as we saw in that example. On step 5, we give our conclusion about the null, or rather we make a decision about the null. And on step 6, we give our conclusion. We're going to look through another example now of a one-way ANOVA, but this time we're going to start from just from the raw data or from the summary statistics that are given below. So in this example, we have a clinical study was conducted to see whether an antibody called denosumab, I haven't learned how to pronounce that yet, which is kind of sad, is effective in the treatment of osteoporosis of postmenopausal women as reported in the article given below. Okay, so we have postmenopausal women with osteoporosis were randomly assigned into groups that received either a placebo or a 6-month regimen of the drug at 14 milligrams, 60 milligrams, 100 milligrams, or 210 milligrams. The following table provides the summary statistics for the women in each treatment group. Okay, and then we have a variety of questions that we are interested in answering based off of this information. Okay, so we're given some other summary statistics in this exercise. So we have SSTR and we have the sum across J of NJ minus 1 times SJ squared is equal to 5,586.36. So this is actually the definition of the SSE. So this is giving us SSTR and the SSE directly. So let's see here. Question 1. Okay. I guess I don't really need to use the 1, do I? Because there's only... Is this an observational study or a designed experiment? Okay, so this is a... Right, so in this exercise, the observations or the patients are randomly assigned into one of those 5 different treatment groups. So that would be the that's a key feature of a designed experiment. So this data is being, or the response variable of interest, which is going to be the body mass index, is essentially being found by exposing the patients to each of these different dosages. or each of these different levels. All right. Part B, what is the response variable? So this is going to be body mass index. So the response variable is what we are measuring and what we are actually directly interested in studying. And in this experiment, we want to assess the body mass index of the women in each of the different treatment group. So therefore, body mass index becomes the response variable. Okay. What is the factor? How many levels does the factor have? Okay, so the factor is the dosage level of the denosumab. Right. So the factor is the variable that is essentially partitioning our observations into the different groups. So in this particular case, it's the dosage level because that's how we're separating each of the different observations. Okay, and it has 5 levels. Okay, at the 10% significance level, is there evidence that a difference exists in the mean BMI for women in the 5 different treatment groups? Okay, so we're going to run our ANOVA procedure here. Okay. So as a refresher, we have 4 assumptions. Okay. All right, now we haven't actually looked in depth at how we can check these assumptions, but we'll go through them anyways, just for illustrative purposes. So in this experiment, we have a designed, this is a designed experiment where the patients are being randomly allocated to the different treatment groups. Okay, so therefore, the SRS and the independent samples assumption are both going to be checked off because of the way that the patients are being randomly allocated to the treatment groups. Okay, normality, we won't be able to check this directly from the raw data, so we'll just make a note and we'll say that we can use residual analysis, which we'll cover in the next lecture set, but we don't know right now whether or not this is going to hold. Okay, for constant variance, we can use the rule of 2. So the smallest and largest standard deviations are 4.3 and 5.8. Okay, so we can say S1 equals 4.3 and S3 equals 5.8. Since 5.8 divided by 4.3 is equal to 1.349, which is less than 2, we can assume that the deviations are equal. So that's essentially how the rule of 2 works. You take the smallest and largest standard deviations, you divide the smallest by the largest. If that value is less than 2, then you can assume that the variances are equal. So in this case, it is less than 2. Excuse me. So we can assume, just have to move some stuff around here. We can assume the variances are equal. Okay. So I'll just put a little check mark there. All right. Yes, divide the largest by the smallest. You can also divide the smallest by the largest, and if it's greater than a half, that's the same thing. So it actually, it doesn't matter which way you divide them, they just have to be within a factor of 2. All right, any questions? Okay, so we are going to test that mu1 through mu5 are equal versus the alternative that not all means are equal. Okay. Oh, step 2. Okay, we're running this test at the 10% significance level. All right. Okay, so on step 3, we have to compute our test statistic. So we can construct an ANOVA table. Okay, so what we have to do now is start filling in the table. So the easiest value to knock off first, well, actually, there's two values that are given to us. So from the previous slide, we're told that SSTR is 98.07661. Okay. And we're told that the error, the SSE, though not given to us in expression, is given to us in terms of its defining formula, or in terms of its defining formula. So this value here, 5,586.36, that is the sum of square error. So we have 556.36. Right. Okay, so adding these two numbers together will give us SS total, or the SS total. 5684.437. Okay, now we can work out the degrees of freedom fairly easily. So the degrees of freedom for the treatment is going to be the number of levels minus 1. So we have 5 levels. So 5 minus 1 is going to be 4. The degree of freedom total is going to be the total sample size minus 1. So from the previous table, if we add the 5 sample sizes together for each group, we will get 236. So this is little n. Okay, so therefore, DF total is going to be 235, and the DF error will then be 231. Okay, now we can divide each of the sum of squares by their mean square to get the mean squared treatment and the mean squared error. So the mean squared treatment is going to be 98.07661 divided by 4, which is 24.51915. And the sum of square error is going to be 5,586.36 divided by 231, which is 24.18338. Okay, and then the F statistic is going to be the mean squared treatment divided by the mean squared error. So that's going to be 1.014. Okay, any questions? All right. Okay, so now all we have left to do is conclude the test. So we can take either the critical value approach or we can take the p-value approach. Right. Okay, so if we take the critical value approach, we're going to have to find our critical value. So this is going to be an F on 4, 231, and 0.1. All right. Now, we know from the F table, we're not going to be able to get the degree of freedom for 231, we're going to have to round down. Okay, so we're going to use F on 4, 120, 0.1. So if we go to our F table now, okay, so you can see that the highest degree of freedom that we can get to is 120. So once our second degree of freedom goes past 120, we're forced to round down to this value. So we're going to have 4, 120, 0.1, which is 1.99. So our critical value here is 1.99. And here is our rejection region. And then clearly our test statistic is not going to get inside this area. So let's say the test statistic is about here. So we have F equals 1.014. I guess I don't really need to draw the line all the way down. It's just in the marker. There we go. All right, so based off the critical value approach, we're not going to reject. So obviously the p-value approach is going to agree, but we'll still go through it just to see the process. So with our p-value approach, we start by marking down where the test statistic is. Okay, so we're going to have, I think I can write it. I'll write it here. So we're going to have the p-value is equal to the probability that the F value exceeds 1.014. Okay, so then we can say since the probability F exceeds 1.014. Okay, so then we go back to our F table. So we have the same degree of freedom. So we're going to use 4 and 120 degrees of freedom. Okay, so we're going to use this set of numbers here. Okay. So our value 1.014 is smaller than the smallest listed value given in that set of numbers. So therefore, the area to its right must be greater than 0.1. Okay. So since this is greater than 0.1, then the p-value is greater than 0.1. Right. And again, we're using the same degree of freedom for the p-value that we did for the critical value for the exact same reason. We can't, there is no table that gives us 231 for the second DF. So we round down. In this case, we round down to the highest available number, which is 120. Right. Any questions? Okay, so regardless of which approach you take, obviously the conclusion is going to be we do not reject. The test statistic does not get into the rejection region. So our test statistic is smaller than our critical value. And the p-value is greater than 0.1. We designated alpha as 0.1. So the p-value therefore is bigger than alpha. Since the p-value is bigger than alpha, we do not reject the null. Okay, so step 6. What we can say here is, assuming the variable of interest is normally distributed, the data do not provide sufficient evidence to suggest that the mean BMI of women with osteoporosis differs across the 5 treatment levels at the 10% significance level. Okay. Scroll down a little. All right. So that's a complete one-way ANOVA process. Any questions? Excuse me. Okay. So one more illustration. This is a shorter illustration, just going through the writing our conclusion for the hypothesis test based off a computer output. So in this exercise, we have the dataset plant growth is available in R. R is a software language that's commonly used in statistics. It contains weight measurements on 30 plants grown under 3 different experimental conditions. So 10 plants in each condition. Consider the following one-way ANOVA table. Okay, so in this ANOVA table, you can see we have the treatment source, we have the error source, we have the degree of freedom, the sum square, the mean square, the F value, and then in the last column, we're being given the P value. State the result of this hypothesis test at the 5% significance level. All right, so we have alpha equals 0.05. We have the P value a direct p-value is 0.1591. Okay, so therefore, the p-value is less than alpha. So we reject H0. Okay. So we can say at the 5% significance level, the data provide sufficient evidence to suggest that the average weight of the plants in each experimental condition differ. Or sorry. Oh, sorry. I have to so most of this is correct. I just didn't start the sentence early enough. So it should be at the 5% significance level, the data provides sufficient evidence to suggest that there is a difference between the average weights of the plants in each experimental condition. That there is a difference between there is a difference between the average weights of the plants in each experimental condition. Okay, so basically there's evidence that a difference exists between average weight. And you can see that in actually working towards the conclusion here, we kind of automatically touched on a few different steps in the hypothesis procedure. So we have step 2, step 4, step 5, step 6, right? So it's pretty easy to complete the test from the output. All we would have to do is add in the F value on step 3. Right? And then all we would have to do is add in the null and alternative on step 1. And then, of course, the only other thing here is assuming all Any questions? No. If you were given this question and it just said state the result of the test, all you would have to do is give the result. So you can just give the conclusion directly. I realize that writing them all out is a little bit overkill, but it's just to give context as to how the procedure would unfold given the output. But I'll make a note here that this is fine as an answer. Okay, so it's fine to just give the conclusion. No worries. Any other questions? Right. Okay, so that brings us to the end of the lecture set number 4 on one-way ANOVA. So a couple of quick remarks. There's 4 assumptions that are associated with the ANOVA procedure. Again, we have that normality assumption, and then we have the constant variance assumption. So these assumptions would, at least in terms of constant variance, their assumptions are quite strict. So we are assuming that regardless of the number of different populations we have in the experiment, they all have the exact same variance. Okay. The ANOVA uses 2 types of variation to make a statement about the means. So despite the fact that it's called an analysis of variance, it is still a test for determining if a difference exists among a set of population means. Okay. When we reject the null hypothesis from an ANOVA, we are saying that a difference exists. The drawback is that we don't actually know where that difference is. So for example, in the minke whale illustrative example that we used to start the lecture set, and then we completed at the end of last class, we rejected the null. But what we don't actually know is which depths lead to significantly different sizes of the whales. So what we need to do is develop a set of procedures that we can use in order to determine where those differences exist. And that's what we're going to move into in the next lecture set. The other thing that we're going to do is look at residual analysis so that we have another suite of tools to actually check the model assumptions from the ANOVA. All right, and as always, there's a cumulative exercise at the end of the lecture set. This exercise is very similar to what we had just worked through. So we have a set of summary statistics here, and then we need to go through and actually run the ANOVA. The only thing that's different is you actually need to work out the SSTR and the SSE directly from what's given. So there's a little bit more background mathematics here, but it's just to serve as extra practice, essentially. Okay, so we'll move on to the next lecture set now. Wait, what the hell's going on here? Sorry, one sec. There we go. Why can't I go backwards? All right. Okay, so in this lecture set, we're going to talk about two main ideas, and well, which are residual analysis. Excuse me. I thought I was going to sneeze. Oh no, it's weird. Okay. Which are residual analysis and multiple comparisons. Right. Now, there's another topic in this lecture set called contrasts. We require the definition of the contrast in order to set up the multiple comparison. So we're going to talk about these three different ideas, but the key ideas are, again, residual analysis and multiple comparison. We need the contrast to set up the multiple comparison. Okay, so we learned in lecture set 4 that we can write the one-way ANOVA, or we can express a one-way ANOVA model as given in equation 1. So this model says all the values in the population of interest are a function of a mean and a normally distributed error. From this model, we can write down 4 assumptions, which are the simple random sample assumption, the independent sample assumption, normally distributed population, so essentially that all points are normally distributed, and the constant variance assumption. So each of the different populations that we are studying have the same variance. And I illustrated this last time by sketching out a number of different normal curves, and every normal curve has the same spread. So that's the idea. We're placing a population at the center of each mean. All of those populations are normal, so they all have a bell curve, and they're all bell curves with the exact same spread. So there's an illustration of this given when we first discussed the assumptions in lecture set 4. So that is on slide 16 of lecture set 4. Okay. So this effectively illustrates the last 2 assumptions, which are that normality and constant variance assumption. Okay. So we talked about methods for testing the model assumptions last class. The first 2 assumptions, the simple random sample and the independence assumption, we're going to assess those based off of an understanding of where the data came from. There's not much mathematically we can do to assess those 2 assumptions. In terms of normality and the constant variance assumption, we have discussed a number of ways of assessing constant variance. So we can use box plots of each of the different groups and check to see if the box plots are the same length. We can use that Levene's test for homogeneity. This is what SPSS does by default. So you'll learn about that in lab and most likely use that in lab as well, because it's a very easy way to check. And it gives you some statistical verification. We could also use the rule of 2, which we saw an example of in our last exercise. The other thing that we can do is use what are called residuals. The benefit of the residual is that you can actually check the constant variance assumption and the normality assumption at the same time. Yeah. All right, now a residual is an estimate of the error. So you'll recall from equation 1, our error terms, the epsilon ij, these represent the normally distributed, our normally distributed random variable with mean 0 and variance sigma squared. So the idea is, if we compute Eij, which would be an estimate of the epsilon ij, these Eij should have a normal distribution with mean 0 and variance sigma squared. So we can directly compute these Eij values from our data, and then we can do things like build normal probability plots of the Eij, or build histograms of the EIJ, and they should be normally distributed. So the probability plot would show you a straight line. And the histograms, if we were to separate by population, should be a bell curve centered at 0 in each case. No, sorry. We would build one histogram of all the EIJs, and it should be a bell curve. Okay, so we can take the epsilon IJs and study them directly as a whole, which is a nice benefit as well. Okay, so to illustrate how this would work, we're going to consider the following toy data set, or the following illustration. In this illustration, we have a researcher is interested in determining if there is a difference between the average amount of time spent downloading a file at 3 different times of day, 7 a.m., 5 p.m., and 12 a.m. Okay, to test the hypothesis of interest, the researcher downloaded the same file 16 times at each time points. Okay, the table below gives the raw data and some summary statistics. So we have 3 treatment groups, which are time of day. So we have 7 a.m., 5 p.m., and midnight. For each of the different times of day, the same file was downloaded 16 times. The time to download the file in seconds is given, right? So we have 16 different times representing how long it took to download the file. At the bottom of each column of time, you have the summary statistics X bar and S. So we have the sample mean and the sample standard deviation for each set of download times. Okay. Any questions? Okay, so this is obviously, or it should be fairly evident that if we wanted to test for a difference between the average download time at each time a day, an ANOVA would be a natural statistical process to consider, because we have 3 different means and we want to look at it for a difference between those 3 different means. Okay, so suppose the results from a one-way ANOVA give evidence that a difference exists. Okay, so if we were to submit the data above to an ANOVA, we end up with an F value of 45.979. So an overwhelmingly large F value, so very clear evidence of a difference. Is the conclusion valid? So again, whenever we ask about validity, we're talking about the assumptions of the procedure holding. So are we finding evidence given that those assumptions are intact? Okay, so let's suppose that we have independent samples and they are simple random samples for illustrative purposes. Okay, so we're going to focus on the normality assumption and the constant variance assumption. So to check the normality assumption and to check the constant variance assumption, we can construct our residuals for this procedure. All right, so in the table below, the residual, an example of how those residual values are constructed is given. So recall, first of all, that the residual is EIJ equals XIJ minus X bar J, right? So in the third column here, the third column for each group, so here, here, and here, we are simply taking the observed value and subtracting the sample mean to get the residual, right? So E1 is equal to 68 minus 113.375 equals negative 45.375. Sorry, this would be E11. Okay. Similarly, E12 is equal to 138 minus 113.375 equals 24.625. E13 is equal to 75 minus 113.375 equals negative 38.375. Okay, and then that same process continues all the way down the line. In the second column, we would technically have E21. Okay, and this would be, oh, sorry, I wrote the, I wrote the abbreviation backwards. So this would be, I'm doing group second. Okay, there we go. Okay, so this one is a little harder to see. I'm kind of crouching it in there. So this would be E12, E22, E32. All right. So I realize that's a little hard to see, but the point is basically that for each observation in each group, we just subtract the sample mean, and that's how we build the residual term. Okay, and it would be the same thing for the 12 a.m. group as well. So just for completeness sake, I'll write it over here so it's legible. So this is going to be E13, E23, E33. This. The way that I have them now should be fine. So the group is the second digit and the first digit is the observation number. Any questions? Okay. All right, so now that we have the residuals computed, so we have our 3 columns of residuals, we can check the normality assumption and the constant variance assumption using these quantities. To check the normality assumption, we actually can just take all of the residuals, pool them together as one large collection of values. So in this case, we would have 48 values. And we can build a normal probability plot of those residual terms. So on the y-axis in this illustration, we have the EIJ, and we're plotting all 48 residual terms against the quantiles of the normal distribution. All right. Now, because the error term is written or assumed to be normal 0 variance sigma squared, the residual should be normal with mean 0. So we can't really pull out the mean directly from the QQ plot, though you can see 0 is sort of centered at the middle of the estimated values. But the key here is that the residuals appear to follow a straight line pattern with the quantiles of the normal distribution. Right, so by plotting the residuals against the quantiles of the normal distribution and observing that straight line pattern, this gives us a process for checking for normality. And this is typically how we would check for normality when we are running a one-way ANOVA. Right? Any questions? Okay. Now, to check for constant variance, I'm giving one example of a way we can do this, but there's so many different ways that we can check the constant variance assumption within the ANOVA procedure. For example, again, we can use that rule of two, perfectly valid and acceptable procedure. We had an illustration of that in the exercise at the end of lecture set 4. If we have the residual values, we can also basically just plot or create box plots of the residual values at each of the different groups and check to see if those spreads are roughly the same. We could also compute the standard deviation of the residual value in each group and then use the rule of two. We could use a Levine's test on the observations in each group or on the residuals in each group. There's a lot of different ways that you can check. On slide 7, I'm giving one example of a way that we could do this. And this is a very basic example, but the idea here is you take the residual value, okay, so our EIJ, right? And you, for each of the different means, you plot the associated residuals. Okay, so this is going to be X bar 1, which was equal to 113.375. Right here we have X bar 2, which was equal to, or no, sorry, this would be X bar 3. Which was 193.063. Okay, and here we have X bar 2, which is 273.25. Okay, and now the process of checking for equal or constant variance here is very, it's kind of naive, but it can work. So we take the largest and the smallest points, okay, and we can draw horizontal lines through them. And then the question is basically, is the gap between that largest and smallest point the same? So do we have the same range for each of the different groups? Okay. So we can write, let this represent the range of each group if all ranges are equal, then assume constant variance. Okay, so let the difference between the two, those sets of horizontal bars be the range, which they are by definition. If those ranges are all equivalent, we can say that the variance is constant. And this works because each group should have mean 0. So if the ranges are the same, that would imply that we have the same spread around 0, which would mean that the variances are equal. All right. Any questions? All right. All right, so residual analysis is a tool that we can use to validate the normality and constant variance assumptions from a one-way ANOVA procedure. We can actually use them across all the different ANOVAs we're going to talk about, but we'll see examples of that a bit later. In particular, the residual analysis is very useful for validating the normality assumption. So this is the most common use of the residual analysis of residual analysis for the ANOVA experiments, right? So the computation of the residuals and then constructing a normal probability plot and using that normal probability plot to assess normality of the response. We could also run tests for normality on the residuals directly. This might be something that SPSS produces automatically. I can't quite remember, but it's just another option. But most often you'll be computing normal actually, in all situations that we use in ANOVA, you will learn how to compute the residuals and construct a normal probability plot for the residuals. So this is one of the key aspects of the lab study of the ANOVAs. Okay, so when we use the normal probability plot, we use it in the same way that we do in any other situation. We just want to see a straight line relationship between the residual values and the quantiles of the normal. If we want to use the residuals to check for constant variance, again, there's a variety of different ways that we can do this. If we decide that we want to use plots, we're basically just plotting the residuals against their treatment group mean or against their treatment group label. And then we want to see an equal deviation for each of those groups. But again, the other processes we talked about, like Levine's test or the rule of two, those would work fine as well. Just multiple ways of checking the same thing. So you can use a few of them to verify that that assumption is intact. And that's never a bad thing to have a couple of different ways to check a result. Any questions? All right. Okay, so now we can get into the key topic from this lecture set. So as I had mentioned at the start, there are two sort of key topics that we want to discuss, which are residual analysis, which we just finished, and the definition of a multiple comparison. Now, before we define the multiple comparison, we have to define what is called a contrast. A contrast, very simply, is a comparison of population means where each population mean can contribute a different amount of information to the contrast or to the comparison. So this tends to be a trickier unit for students to wrap their heads around. I think that the rationale is because we typically use fractions to express the contrast coefficients. So those capital C values that are listed in the equation on slide 9. So we'll go through a few different examples of just setting up contrast to try and clarify how this works. And then we will look at direct examples of how we can work with the contrast in the context of a hypothesis test and a confidence interval. So we won't rush this section. We'll spend as much time as we need to try and get this idea defined. Once we have the contrast down, we can easily transition this into a multiple comparison, as the multiple comparison is actually just a special type of contrast. All right, so why do we need to learn about a contrast? Well, we know that when we run an ANOVA, if we reject a null hypothesis from the ANOVA, that means that there's evidence that a difference exists. The issue is we don't actually know where that difference is, right? So say we have 4 population means, we reject the null hypothesis, and we know a difference exists. We don't know if mean 1 is different from mean 3, or if mean 2 is different from mean 4, or if mean 1 is different from all of the other means. It could be that only 2 means are different. It could be that all the means are different. So we need to have a method for actually checking where the difference exists. And that's where the contrast comes in. So contrasts give us a tool for checking where those differences exist. All right, now what a contrast is a linear combination of the treatment means. So the general contrast, which, or the population contrast, which we designate as gamma. Okay, so this symbol here is gamma. This has the same representation as mu. So mu is a population mean, gamma is a population contrast. All right, so we want to, inevitably, we're going to learn how to estimate gamma. So the same way that we learned how to estimate mu using X bar, we're going to learn how to estimate gamma, and we're going to have a symbol to represent that estimate, which I think I call little c. Very creative symbol, small contrast, sample contrast. All right, so what does it mean to be a linear combination? It means that associated with each of the means in the experiment is a constant that we call capital C. And the capital C's have to add to 0. Okay. So and the other thing is that the means have to be linear. So they're all to the power of 1. So a valid contrast is one where all of the coefficients add to 0 and the means are linear. So they're not any other type. The means can only be added and subtracted, and they all have to be to the power of 1. You can't have like C1 mu1 squared minus C2 square root of mu2. That would not be a valid population contrast. You could technically use that expression, but that doesn't fit within the definition of the contrast that we are studying. So all of the coefficients have to add to 0, and all of the means have to be untransformed, essentially. Right. Any questions? Okay, so we're going to recall or turn our attention back to that minke whale exercise that we used in lecture set number 4. Okay, so we have 4 different treatment groups where each group represents the depth in the ocean at which the whale was entangled. We are going to use the definition of each of those groups to set up 3 different kinds of contrasts so that we can get an idea for how this is going to work. All right, so I'm going to summarize the data from the whale example momentarily. Let's just start with exercise A, and then we'll work our way down from that definition. So part A says, set up a population contrast that compares the average body length of minke whales entangled at depths of 0 to 99 meters to whales entangled at depths of 150 to 99. All right, so this is going to work as follows. First, let's just recall the structure of the problem. So we can summarize the experimental design as follows. Okay, so we have length of minke whale. Okay, and then we're going to have mu1, mu2, mu3, mu4. Average length. And then here we're going to have depth. which is also the factor. Okay, sorry, one sec. I hate that I had to squeeze this all. I'm gonna move this down. Okay. Okay, so we had 4 different depths, which were 0 to 50 meters, or 0 to 49 meters. $50 to 99 meters, 100 to 149 meters, and 150 to 199 meters. Okay, so we have 4 population means. We want to set up contrast comparing the means based off the descriptions given above. So in part A, it says, set up a contrast that compares the average body length of minke whales entangled at depths of 0 to 99. So we're crossing 2 groups here to the whales entangled at 150 to 199. So we're excluding group 3, and we want to take the average of group 1 and group 2. All right, so the way that this is going to work is first, we'll define the general form of the contrast. So we're going to have gamma is equal to C1 mu1 plus C2 mu2 plus C3 mu3 plus C4 mu4. Okay, so we want, we'll just make a few notes. Average of mu1 and mu2 versus mu4. Okay, so this is what we're looking for based off the description. So we want to take the average of mu1 and mu2, and we want to compare it to mu4. All of the coefficients have to add to 0. Okay. Right. And we can't transform the means, which is fine because we don't need to ever in the contrast. Okay, so we need C1 to C4 to equal 0 when we add them together. We want to take the average of mu1 and mu2 and compare it to mu4. So this is how we can do this. First, to take the average of mu1 and mu2, we write let C1 equal C2 equal 1/2. Okay, so we have 1/2 plus 1/2 is equal to 1. We don't need mu3. So we make C3 equal to 0. So we're knocking mu3 out. And now we want to compare to mu4. We can compare to mu4 by setting C4 equal to -1, because a half plus a half is +1. +1 minus 1 equals 0. Okay, so that gives so therefore C1 plus C2 plus C3 plus C4 is equal to 1 over 2 plus 1 over 2 plus 0 minus 1 equals 0 as required. And then gamma is going to be 1 over 2 mu1 plus 1 over 2 mu2 minus mu4. Okay, so like, again, what we're trying to do here is take the average of mu1 and mu2, right? So I want to contribute equal amounts of information from mu1 and mu2 to the contrast. So if I want the average of two means, how would I get that? I would say mu1 plus mu2 divided by 2, right? Does that make sense? Okay, so if I have mu1 plus mu2 over 2, that means that the coefficient associated with each mean has to be a half. Does that make sense? And then just mu1 plus mu2 over 2 is mu1 over 2 plus mu2 over 2, right? And then mu1 over 2 is the same thing as a half times mu1. That's their equivalent. Does that make sense? Contrasts. Okay. Okay, so pretty good process or progress. We finished the ANOVA. We talked about residual analysis today, which is good. So that's going to cover everything you need in lab once you get to ANOVA, which I imagine will be next week. And by that time, we should be done comparison and contrast at the end of the class on Tuesday. And then on Thursday, we have our first term test or our first quiz. Sorry, quiz. It's a quiz. I sent out some details about the quiz on Tuesday. I'll send out the same details again as a reminder. There are practice problems available on the course website for the quiz. And it's going to cover lecture sets 1, 2, 3. So it's basically a quiz that's reviewing t-test and confidence intervals and covers the material that's on assignment number 2. So you should have the solutions to assignment 2, or I'll post the solutions to assignment 2 after Friday when it's handed in. That's another reminder, assignment 2 is due tomorrow. And hopefully you'll have your grades back by then, but I can't promise that. Okay, so that's everything for today. And if you have any questions, I'll hang around. I have office hours tomorrow, and otherwise I will talk to you guys on Tuesday. You guys too. Take care.